Welcome to Tech with Koushik. This is set 7 of our AI-200 Microsoft Certified Azure AI Cloud Developer Associate Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link is in the description. Let us begin set 7. Work through question number 240. Step by step. This one tests your understanding of app config labels. First, locate the key operational constraint. The same application key model. Endpoint needs one value in development, another in staging, and another in production. The team wants to keep the key name stable. Which Azure app configuration feature is designed for this variation? Now compare the choices one requirement at a time. Option A is labels. Option B is event grid retries. Option C is redis STTL. Option D is Kubernetes liveness probes. The correct choice is option A, labels. Labels let multiple app configuration key values share the same key while carrying environment dash, version dash, or deployment-specific variants. The remaining options fail one or more requirements because B, event retries do not version configuration values. C, redis STTL controls cache lifetime. D, health probes do not select application configuration variants. Use app configuration labels when the same key needs environment or version-specific values. Approach question number 241 by checking every constraint. Identify the decisive constraint before considering the options. A Python application uses the Azure App Configuration Provider and must load feature flags and allow those flags to refresh at runtime. Complete the provider settings. For the first statement, evaluate, enable feature flag loading with the blank. Eliminate between 1. Feature underscore flag underscore enabled equals true, feature underscore flag underscore enabled equals false, or key vault underscore credential equals none. For the second statement, evaluate, enable runtime feature flag refresh with the blank. Eliminate between 2. Feature underscore flag underscore refresh underscore enabled equals true, feature underscore flag underscore refresh underscore enabled equals false, or trim underscore prefix is sad face. For statement 1, the best fit is feature underscore flag underscore enabled equals true. The Python provider loads feature flags when feature underscore flag underscore enabled is enabled. For statement 2, the best fit is feature underscore flag underscore refresh underscore enabled equals true. Feature flag refresh is independently enabled through feature underscore flag underscore refresh underscore enabled. A useful exam pattern is this. Loading feature flags and refreshing feature flags are separate provider behaviors. Let's analyze question number 242. We are moving to app config refresh. Review the scenario and identify what must be achieved. An application uses Azure App Configuration for several runtime configuration patterns. Drag each app configuration capability to the behavior it provides. Use each destination exactly once. Start with these movable items. The first source candidate is label selector. The second source candidate is configuration refresh. The third source candidate is feature flag refresh. The fourth source candidate is key vault reference. Now identify the requirement represented by each destination. Requirement A, resolve a configuration key to secret material stored in Azure Key Vault. Requirement B, reload changed key values without redeploying the application. Requirement C, choose an environment or version-specific variant of a key. Requirement D, update loaded feature flags independently from normal configuration refresh. For mapping 1, label selector satisfies choose an environment or version-specific variant of a key. For mapping 2, configuration refresh satisfies reload changed key values without redeploying the application. For mapping 3, feature flag refresh satisfies update loaded feature flags independently from normal configuration refresh. For mapping 4, key vault reference satisfies resolve a configuration key to secret material stored in Azure Key Vault. The requirement to solution match is labels select key variants. Configuration refresh rechecks key values. Feature flags have their own refresh behavior, and key vault references keep secret material in Key Vault. Watch for this clue in similar questions. App configuration has distinct mechanisms for selection, refresh, feature management, and secret references. Focus on the key wording in question number 243. This scenario tests whether you recognize the controlling constraint. An application loads Azure App Configuration values and encounters a key vault reference. The actual secret must remain stored in key vault. Which two statements are correct? Select two. More than one answer may be correct, so evaluate every option. Focus on which option satisfies the complete requirement. Option A. The app configuration value can store a reference to the key vault secret instead of the secret material. Option B. The application/provider must have a credential or secret client path that is authorized to resolve the referenced key vault secret. Option C. Copy the secret value into a normal app configuration key, so key vault is no longer needed. Option D. A key vault reference automatically grants the application permission to read every secret in the vault. Option E. Key vault references require the secret to be embedded in the application image. After checking every constraint, choose Option A. The app configuration value can store a reference to the key vault secret instead of the secret material, and Option B. The application/provider must have a credential or secret client path that is authorized to resolve the referenced key vault secret. The key clue points here because app configuration stores the reference metadata, while the client/provider resolves the target secret from key vault using an authorized identity or configured client. Here is how to rule out the alternatives. C. The design goal is to keep secret material in key vault rather than duplicate it as a normal setting. D. A reference does not grant authorization. Key vault access must still be configured. E. No secret needs to be embedded in the image. Remember this decision rule. A key vault reference separates where configuration is discovered from where the secret is securely stored and authorized. For question number 244, separate the requirement from the distractors. Next, we enter the topic of OTel custom spans. Pay attention to qualifiers such as least, most, and minimum. Automatic instrumentation does not capture a custom document ranking stage inside a Python API. The team wants that stage to appear as its own operation segment in the distributed trace. Which OpenTelemetry action should the developer take? Eliminate every option that violates even one requirement. Consider Option A. Create a custom span with the application's tracer around the ranking operation. Consider Option B. Add a red ISSTTL to the ranking result. Consider Option C. Create an Azure resource lock. Consider Option D. Write only a KQL query without instrumenting the code. The best answer is Option A. Create a custom span with the application's tracer around the ranking operation. The decisive reason is a custom span models application work that automatic instrumentation does not already represent and becomes part of the end-to-end trace. Check why each remaining option is not the best fit. B. Cache expiration does not add tracing information. C. Resource locks protect management operations, not traces. D. KQL can analyze collected telemetry, but cannot create missing spans retroactively. Exam strategy. Instrument first with OpenTelemetry. Query the resulting telemetry later with KQL. Let's break down question number 245. Start by separating the facts from the requirement. A request crosses multiple instrumented services in a distributed AI application. For each statement, select yes if the statement is true. Otherwise, select no. Statement 1. Test this claim. Spans that belong to the same distributed trace share the same trace identifier. Statement 2. Test this claim. If trace context is not propagated across a service boundary, downstream telemetry can appear as a separate trace. Statement 3. Test this claim. Every span in one trace must have the same span identifier. After checking the full claim, Statement 1 is yes. A trace ID correlates spans that belong to the same end-to-end transaction. After checking the full claim, Statement 2 is yes. Propagation carries the parent trace context across process and network boundaries. After checking the full claim, Statement 3 is no. Each span has its own span ID, even when several spans belong to the same trace. Use this elimination rule in the exam. Trace ID correlates the transaction. Span IDs identify individual operations inside it. Next is question number 246. The focus now shifts to OTel span attributes. Review the scenario. A Python service exports OpenTelemetry spans to application insights. The developer wants to attach a business identifier and record an exception on a custom span. Complete the instrumentation statements. Statement 1. Identify the clue in. Add the business identifier to the span as of the blank. Compare 1. Span attribute, new trace ID, or KQL table against the requirement. Statement 2. Identify the clue in. Capture the handled exception on the span by using the blank. Compare 2. Span.record_exception, x, bin, time generated, 5m, or expire against the requirement. After elimination, Statement 1 uses span attribute. Span attributes are exported as custom properties and can carry application-specific context. After elimination, Statement 2 uses span.record_exception, x. Record_exception attaches exception information to the current span. Use span attributes for diagnostic context and span exception recording for failures within traced work. Start by identifying the requirement in question number 247. Read the scenario with the target outcome in mind. An API calls a worker service, which then calls a database. Operations needs one end-to-end trace that shows latency across all three components. Which two implementation practices are essential? Select 2. Choose every applicable answer and reject partial matches. Check each option against the exact requirement. Choice A. Instrument the participating services with OpenTelemetry tracing. Choice B. Propagate trace context across the API to worker and worker to database boundaries where applicable. Choice C. Generate an unrelated trace ID independently in every service. Choice D. Collect only CPU metrics and disable traces. Choice E. Remove parent-child relationships between spans. The correct selections are Option A. Instrument the participating services with OpenTelemetry tracing, and Option B. Propagate trace context across the API to worker and worker to database boundaries where applicable. Here is the reasoning that confirms the answer. Distributed tracing requires instrumentation that emits spans and context propagation that keeps downstream work correlated with the originating trace. Now eliminate the distractors. C. Independent trace IDs break end-to-end correlation. D. Metrics alone do not provide request-level distributed trace structure. E. Parent-child relationships help represent the causal operation chain rather than preventing it. A useful exam pattern is this. OpenTelemetry distributed tracing is instrumentation plus context propagation. Question number 248. Find the decisive clue before choosing. This question moves us into KQL failure analysis. Look for the wording that eliminates the distractors. Application insights data is stored in the workspace-based app requests table. An engineer needs the number of failed requests by request name during the last hour. Which KQL query best satisfies the requirement? Compare the options by fit, not by familiarity. Next, Option A. App requests where time generated ago 1H and success equals false summarize failed count equals sum item count by name. Next, Option B. App requests where success equals true project name. Next, Option C. App requests summarized by time generated. Next, Option D. App dependencies where success equals true take one. The required response is Option A. App requests where time generated ago 1H and success equals false summarize failed count equals sum item count by name. This option satisfies the complete requirement because the query applies the time and failure predicates, then aggregates represented request count by name. The incorrect choices are plausible, but unsuitable because B. It selects successful requests and does not aggregate failure counts. C. Grouping by raw time generated does not calculate failures by request name. D. It queries dependency telemetry rather than failed request telemetry. Watch for this clue in similar questions. 4KQL troubleshooting. Filter the correct table first, then summarize by the dimension the question asks about. Question number 249 contains an important exam distinction. Focus on the requirement that drives the design choice. An engineer is analyzing request latency in the app requests table. For each statement, select yes if the statement is true. Otherwise, select no. Now evaluate statement 1. Summarize average, duration ms, by bin, time generated, 10m, groups request duration into 10-minute time buckets. Now evaluate statement 2. Grouping directly by raw time generated automatically creates 10-minute buckets. Now evaluate statement 3. Percentiles, duration ms, 50, 95, 99, can return multiple latency percentiles for the grouped requests. For the first statement, choose yes. Bin rounds timestamps into the requested interval before summarize groups the rows. For the second statement, choose no. Raw time-generated values are highly granular and do not automatically form 10-minute groups. For the third statement, choose yes. KQL percentiles can calculate several requested percentile values in one aggregation. Remember this decision rule. Use bin, for time buckets, and percentiles when tail latency matters more than the mean. Question number 250. Tests careful elimination. Look for the wording that eliminates the distractors. An Application Insights workspace contains failed requests in app requests and exception telemetry in app exceptions. The engineer needs to identify exceptions that belong to the same failed operations during the last hour. Which KQL technique is the most appropriate? Watch for distractors that are valid services but wrong for this scenario. Consider option A. Filter both tables to the time window and join them on operation ID. Consider option B. Sort each table alphabetically by name and assume matching row positions are related. Consider option C. Use bin, duration ms, 1h, as the only correlation key. Consider option D. Query app requests only because exception telemetry cannot be correlated to requests. The option that satisfies the complete requirement is option A. Filter both tables to the time window and join them on operation ID. Application Insights tables carry operation ID for operation-level correlation, so joining filtered requests and exceptions on that identifier links telemetry from the same operation. B. Alphabetical order has no causal relationship to telemetry correlation. C. Duration buckets can contain many unrelated operations and are not a correlation identifier. D. Application Insights operation identifiers enable cross-table correlation. Exam strategy. When correlating Application Insights telemetry with KQL, prefer operation identifiers over timestamps or display names. You have completed Set 7 of the AI-200 Microsoft Certified Azure AI Cloud Developer Associate Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Koushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.